All right, let's get right into it. Welcome back, everyone. Today, we're acting as your exam strategists for Cambridge AS and A-level physics, specifically subject code 9702. Look, we all know it's super easy to just overload your brain with raw physics facts, right? But if you don't have the strategy to actually analyze and apply them when the clock is tickling, well, you're going to lose marks. So today, we're changing the game. We're breaking down density, pressure, and the sometimes tricky rules of equilibrium. We are going to find the back door into every single question on these topics. We're turning dense textbook formulas into razor-sharp tactical tools. Work smarter, not harder. That's how we secure those top grades. Let's do this. Okay, quick look at the roadmap for today. We've got 4 main stops. 1, building the toolkit. 2, the why of upthrust. 3, the rules of equilibrium. And 4, exam challenges. Let's keep moving.
Starting off with Section 1, building the toolkit. Let's get our foundational formulas locked in.
Now, I know these foundational formulas look incredibly simple, but trust me, they are literal traps under exam conditions. First up, density, the Greek letter rho. It's rigorously defined as mass per unit volume, so rho equals m over v. And hey, the standard SI unit here is kilograms per cubic meter. Pro tip for the exam, always check your units. If a question throws grams and cubic centimeters at you, convert them immediately, don't fall for it. Then we have pressure. Pressure is the force acting perpendicularly per unit area. P equals F over A. The unit is the Pascal, which is exactly 1 Newton per square meter. Now, I really want to emphasize that word, perpendicularly. If they give you a force applied at an angle, you've got to resolve that force into its vertical and horizontal components. You only use the perpendicular one to find the pressure. It's a classic examiner trick to test if you're actually paying attention.
All right, stepping up the complexity a bit, let's talk about pressure inside a fluid. When you're looking at a point, let's say at a depth h below the surface, the pressure is caused by the literal weight of the liquid column directly above it. That gives us our first major equation. Pressure P equals rho times g times h. Rho is liquid density, g is gravity, h is depth. Easy, right? But wait, here's the ultimate trap. The formula rho gh only gives you the pressure due to the liquid itself. If the exam asks for absolute pressure or total pressure, you cannot forget the massive atmosphere pushing down on the top of the liquid. Absolute pressure is atmospheric pressure, PA, plus that liquid pressure, rho gh. Worked example 4F in the textbook perfectly highlights this trap. It asks for the excess pressure over atmospheric, which is just rho gh. But man, if it had asked for total pressure, you'd have to add that 1.01 times 10 to the power of 5 pascals of atmospheric pressure. Missing that single simple addition? Yeah, that literally costs students entire grade boundaries. Don't let it be you.
Moving on to Section 2, the why of upthrust. We know things feel lighter in water, but we need the physics proof. So examiners don't just want you to state that objects float, they want you to prove exactly why. Let's visualize a cylinder submerged in water and walk through the logic. Step 1. Like we just said, pressure in a liquid goes up as you go deeper. Therefore, the pressure acting on the bottom of our cylinder is mathematically greater than the pressure on the top. Make sense? Step 2. Since pressure is force over area, that higher pressure on the bottom means there's a larger upward force pushing on the base compared to the downward force pushing on the top. Step 3. The difference between those two forces? That is exactly what upthrust, or buoyancy, is. When you crunch the numbers, taking the pressure difference and multiplying by the area, you get this beautiful equation. Upthrust force equals rho times g times v, where v is the volume of the displaced fluid. And since density times volume is mass, rho times v is the displaced mass. Multiply that by g, and boom, you have the weight of the displaced fluid. It's a really elegant piece of physics. It takes pure fluid mechanics and directly proves Archimedes' principle. Just brilliant.
All right, Section 3, the rules of equilibrium. Let's talk about keeping things perfectly balanced. Listen, for an object to be in a state of true static equilibrium, there are strict, non-negotiable rules. You literally have to memorize these for those crazy diagram questions at the end of the paper. Rule 1. The sum of the forces in any direction has to be exactly 0. Resolve vertically, up perfectly cancels down. Resolve horizontally, left perfectly cancels right. Rule 2. The sum of the moments about any point must be 0. Remember, a moment is just the force times the perpendicular distance to the pivot. So the principle of moments means total clockwise moments must equal total anti-clockwise moments, period. Oh, and if you see a couple, two equal but opposite forces that don't line up, the torque of that couple is just one of the forces times the perpendicular distance between them. Bottom line, equilibrium means 0 net force and 0 net turning effect, absolutely 0.
And now, Section 4, Exam Challenges. Let's put this toolkit to work on some real Cambridge source questions.
Okay, let's jump into worked example 4G. It asks us to calculate the force needed to lift a metal cylinder when it's just sitting in air, and then calculate it again when it's completely submerged in water. They give us the volume, 0.50 cubic meters, the metal's density is 7,800 kilograms per cubic meter, and water is 1,000. Before I show you the answer, pause for a second. Which formula from our toolkit are you going to grab first for part A?
Got it? Okay, let's break it down. To find the lifting force in air, we basically just need the cylinder's weight. Weight is mass times gravity, right? And mass is density times volume. So step 1, force in air is the volume, 0.50, times the metal's density, 7,800, times 9.81 for gravity. That punches out to 3.8 times 10 to the power of 4 newtons. And yet we ignore the air's upthrust here because, honestly, air density is basically nothing compared to solid metal. Step 2, what about in water? The force needed is going to be its true weight minus the upthrust from the water. So let's calculate that upthrust using our new best friend, rho g v. We use the water's density this time, so 1,000 times 9.81 times the volume of the displaced water, which is the whole 0.50 cylinder. Step 3, just find the difference. Take the original weight, subtract that upthrust, and you get 3.3 times 10 to the power of 4 newtons. The force required is less, which totally validates Archimedes' principle in action.
All right, time to level up. This is end of topic questions 16. It's one of those classic, terrifying uniform beam diagrams. We've got beam AC attached to a wall at point A. It's propped up by this rigid bar BD. The beam is 0.40 meters long, weight W is unknown. Hanging off the end at C is an empty 12-newton bucket. Meanwhile, the rigid bar is pushing up with 33 newtons at a 52-degree angle, and the whole thing is perfectly in equilibrium. Now, put your exam strategist hat on. Look at this diagram. Your first major goal is deciding where to place your pivot point to make the math as lazy as possible. Where are you putting it?
Okay, here's the mental scaffolding to absolutely hack this question. Step 1, put the pivot at A, right at the wall. Why? Because the wall is exerting all these unknown messy forces to hold the beam up. By making A our pivot, the distance for those unknown forces becomes exactly 0. Boom! They are entirely wiped out of our moments equation. Tactical genius, right? Step 2, we have to handle that 33 Newton angled force. Remember the golden rule? Moments need perpendicular distances. We only want the vertical push. Quick bit of trig, 33 times the sine of 52 degrees gets us the vertical component. Step 3, equate the moments. Clockwise equals anticlockwise. What's pulling it clockwise? The beam's weight, W, acting right in the middle, so at 0.20 meters since it's a uniform 0.40 meter beam, plus that 12-newton bucket acting at the very end at 0.40 meters. And what's pushing it anticlockwise? That vertical component of the 33-newton force we just found acting at 0.30 meters. Set those equal, and suddenly you have a super basic algebraic equation where W is the only unknown. Solve for W, and you just bagged maximum marks. Let's do one more heavyweight problem. End of topic question 3. I actually love this one because it mashes fluid mechanics and static equilibrium together. We have a metal drum, volume of 0.500 cubic meters, weight of 800 newtons. It's being pinned down 300 meters underwater by a cable tied to the seabed. Seawater density is 1,030 kilograms per cubic meter. The big question, what on earth is the tension in that cable?
Don't panic, just systematically deconstruct the forces. It's tied down securely, which means it's in equilibrium. Total vertical forces must be 0. Let's look at downward forces first. We've got the drum's actual weight pulling down, which is 800 newtons. And we've got the cable's tension pulling down. Let's just call that T. Now, what's pushing up? That would be our upthrust from the displaced seawater. Grab the formula, rho times G times V. That's 1030 for the seawater, times 9.81, times 0.500 for the volume. That spits out a massive upward force of 5,052 newtons. Finally, apply the rule, upward equals downward. So 5052 newtons up equals 800 newtons down plus our unknown tension T. A little quick subtraction and we see T has to be 4252 newtons, round it to 4.3 kilonewtons, and you're done. By just sticking strictly to the toolkit, a scary deep-sea physics problem becomes a total piece of cake.
All right, to really cement this in your brain before the exam, I've built this visual cheat sheet for you. Density, mass over volume. General pressure, perpendicular force over area. Liquid pressure change, rho times G times depth change. And upthrust, rho times g times volume. When you sit down in that exam hall, you need to be able to close your eyes and see this exact matrix. Notice how they all link together? Density feeds into liquid pressure, which feeds straight into upthrust. Seeing those connections is how you keep from drowning in a sea of random algebra.
And I really want to call out this specific quote from the textbook. A fluid that is at rest has all points in the fluid in equilibrium. This single sentence just beautifully ties together everything we've done today. Fluid mechanics and static equilibrium, they aren't separate things. A stationary liquid is just billions of tiny particles all following the rule of zero net force. Grasping that concept gives you such a better, deeper understanding of why equations like pressure equals rho gh actually work in the real world.
Okay, we're wrapping up our technical breakdown, but I want to leave you with a bit of a brain teaser. Picture an object fully submerged in a tank of water. Out of nowhere, a massive weather system moves in, and the absolute atmospheric pressure pushing down on the tank skyrockets. My question to you is, does the upthrust acting on that submerged object change? Think really carefully about the exact formulas we used today. Does upthrust care about the absolute total pressure, or does it only care about the difference in pressure between the top and bottom? Check your notes, write out your logic, and see if you can prove it to yourself. Good luck studying, and I'll catch you in the next explainer.